focusing on Jupiter ultraviolet Aurorae. From there, he moved to Dublin Institute for Advanced Studies as a postdoctoral scholar. Matthew's research focuses on how internal and external drivers balance one another in the Jupiter's magnetosphere, and involves UV and X-ray auroral observations, in situ spacecraft measurements, and solar wind models. Through this, Matthew have focused also on adopting modern statistical techniques and machine learning methods with uncertainty quantification, which we will explore in the next position, AI-based. So you have seen Aurora's pictures everywhere in the news this week. We're just going to see them from different planets. And the topic of today is casting new light on Jupiter's unexplored XUV Aurorae. Thank you. Thank you.
Thank you. Is it
In the,
Sorry,
in the
wait,
Zoom meeting,
Yeah.
it's like this. I don't know why.
I have a question on Zoom.
so that should be
Yes,
good
yeah,
on both
perfect.
ends now?
Yeah.
Cool. Yeah, that should be good. Okay, hopefully everyone can hear me. And yeah, thanks for having me today. Before I get started with the science part of this talk and the kind of engineering part of this talk, I wanted to say that this is very much an ongoing study. This is a study that we're pursuing to use the Chandra X-ray imager, specifically the HRC-S detector, to image in the extreme ultraviolet, the XUV. And so while I'm here for the next 2.5 weeks or so, there's a lot of open questions in this field that I'd be happy to discuss with anybody here. But that said, let's get started. So we're going to be moving from one end of kind of the cosmic scale to the other, talking about one of our nearest neighbors here in the solar system, the planet Jupiter, and a relatively low high energy effect on that planet, which are its soft X-ray, hard X-ray, and extreme ultraviolet emission as measured with Chandra HRC-S. So before I get into that, I wanted to just talk a little bit about the aurora in general, both here on Earth and at Jupiter. They're driven by very similar culprits. Hopefully, in the last year or two, at the solar maximum we've been at, you've been able to see the aurora either here in Boston or elsewhere around the world. If not, this is what the Earth's auroral oval looks like from the south. This is over Antarctica, as measured by the GOES satellite, I believe, in the ultraviolet. So in its most basic form, any aurora that we see throughout the solar system is an atmospheric emission. Generally, it's an emission from excited neutral atoms in an atmosphere, and those neutral atoms or molecules have been excited by accelerated plasma in the near space environment that's being driven into the atmosphere. Because of this, all aurora, regardless of whether you're on the Earth or Jupiter, require a couple main ingredients. You need a neutral atmosphere to excite, you need some source of plasma nearby, and you need a magnetic field to direct that plasma into the atmosphere. Looking at Jupiter's aurora, we're on a completely different scale than the Earth, although the shape of those two emissions looks very similar to one another, at least in broad strokes. At Jupiter, we have these three ingredients. We have a neutral atmosphere, primarily hydrogen, H2 with trace helium. We also have a very interesting source of plasma that I'll get into on the next slide, which is somewhat unique in our solar system. And we have a very strong magnetic field, the strongest of any planet in the solar system. And all of these things work together to create this very vibrant aurora, here imaged by the Hubble Space Telescope in the FUV. So what's driving the aurora at Jupiter? First, we'll look at this figure on the right, which is just a schematic of Jupiter's magnetosphere. This is the region of space near the planet Jupiter, where plasma is governed by Jupiter's magnetic field instead of the sun's magnetic field. Within this purple region, we're looking at kind of the core of Jupiter's magnetosphere. You can see that it's mostly a dipole shape, especially towards the sun, which is off towards the left. As you move down tail in the anti-sunward direction, it gets stretched out into this long kind of cometary tail of magnetic field and plasma. Deep within this magnetosphere is the moon Io. Io, as imaged by the New Horizons spacecraft up there in the corner when it flew by, is volcanically active. It's one of the most volcanically active bodies in the solar system. And between its constantly erupting volcanoes and sublimation of its surface, Io generates about 1,000 kilograms of plasma every second. That plasma initially is moving at Io's Keplerian velocity before it's swept up by Jupiter's very intense magnetic field. Intense for a planet at least. Jupiter's dipole moment is something just over 4 Gauss. This makes it 20,000 times stronger than the Earth's own dipole moment. And what that means for us is when this plasma is created deep in the magnetosphere, it kind of gets locked onto magnetic field lines. It's not going to diffuse away from them. But since it needs to accelerate up to Jupiter's rapid rotation rate, just under 10 hours or about 2.5 times shorter than an Earth day, we're going to generate a lot of energy in this process. That energy ultimately comes from Jupiter's rotation itself, its momentum, but it's conveyed into the plasma in Jupiter's magnetosphere by co-rotation enforcement currents. These travel along Jupiter's magnetic field lines into the equatorial plasma in order to accelerate the iogenic plasma we have here. And this process, instead of a solar wind process like we see at the Earth, is responsible for Jupiter's aurora. So I'd be remiss if I didn't show a video of Jupiter's aurora in the FUV, again imaged with the Hubble Space Telescope. Because this aurora is so bright and observable from the Earth, we can actually create high cadence videos like this that show how the aurora evolves over about 45 minutes real time. If I pause this video, I can label a couple interesting points of this. The first one I'll talk about is the Io footprint aurora. This doesn't matter hugely for the rest of my talk in the X-ray, but it's nonetheless interesting. This is an auroral emission driven by the moon Io on the magnetic field line connecting that moon to Jupiter's surface. A current flows along that magnetic field line, crosses through Io's crust, and flows back, driving that auroral emission. We then have a main oval or main auroral emission. This is the most similar to what we see here on the Earth. It's made of kind of a latitudinally thin but longitudinally extended ribbons or sheets of emission. And even though it looks a lot like what we see on the Earth, it's driven by this different process fundamentally. And because of that, it actually never turns off. Unlike the Earth's aurora, which we see kind of sporadically, and which never shines on the day side during the daytime, Jupiter's main oval is constantly emitting about as bright as the brightest aurora here on Earth. Northward of that main oval, we have the polar dark region and polar active region, which are very interesting as we move into the X-ray. These, as their name suggests, the dark region is an emission where we see very little emission from any wavelength of light. And the active region is just the opposite. We see very bright flares and patchy aurora. Now moving beyond the UV, which is what I've talked about so far today, we also can image Jupiter's aurora in the X-ray, there on the left, and the IR, just for completion here, on the right. In the X-ray, this is an image generated using Chandra data. The kind of red coloring in the back there is the ultraviolet emission shown for reference. I should say all of these images are taken from a vantage where you're now above Jupiter's north pole, looking down on the auroral oval, which makes this kind of kidney bean shape. The X-ray aurora, especially the hard X-rays, these larger green dots in that figure, trace the main emission very nicely. And the soft X-rays, the smaller dots in that figure, trace the active region north of that main emission. We do see some X-rays in the dark region within that main oval, but very few, just like with the ultraviolet. Now, I've kind of summarized some of the wavelengths we're talking about here, as well as the emission processes themselves, but I really want to focus on two. So Chandra can observe something like 1 angstrom through to about 50 angstroms, depending on which instrument configuration you're using by default. The Hubble Space Telescope STIS camera can observe starting at about 115 nanometers, or just over 1,000 angstroms. So there's a huge gap of emission that we can't observe at Jupiter. And this is ultraviolet. Now, I wouldn't be here if we couldn't see that emission at all. But in fact, using a technique that was developed by Jeremy Drake while he was here back in 2020, we can actually use the HRC-S camera of Chandra to observe into this XUV from the X-ray side, probing up to about 200 angstroms, kind of extending that 50 angstrom limit longward. To do this, we need to use the HRC-S detector because of its kind of unique geometry of the UV and ion shield, or UVIS. This shield has two components on the thin detector chip, which is on the middle detector chip, which is what we're going to be mostly focusing on today, which I've shown zoomed in down here. There's this central kind of T-shaped region of thicker UVIS coating. There's an extra layer of aluminum on this coating, and then a thinner region shown in lighter gray surrounding it. This thin region has slightly less aluminum coating and therefore lets through slightly longer wavelengths of light. The effective areas for the thin and thick filter are shown on the right here. The two plots are the same. The y-axis in the top is logarithmically spaced and in the bottom is linearly spaced, but that's the only difference. And as you can see from either of these, right past about 50 angstroms all the way out to the longest wavelengths Chandra can observe rather, we observe more counts when we have the thin filter rather than the thick filter. So by looking off the optical axis of the HRC-S detector in imaging mode, we can observe and take images of Jupiter's XUV aurora. This is really useful thanks to some modeling work done by Sean McEntee as part of his thesis at DIAS. This here, through this maze of plots, we're going to start in the middle. This is the same effective area curve I showed in the last figure or on the last slide. But we can convolve this with a charge exchange spectrum of Jupiter's X-ray emission measured with the XMM Newton spacecraft. This has finer spectral resolution than Chandra does. And so we get all of these points, we can fit them to both a solar wind charge exchange and an Io charge exchange. The difference here being where the plasma comes from and therefore what the species in those plasma are. With these fits shown in kind of purple and teal down here, we can extend the emission into the XUV and convolve it with the HRC-S response at those wavelengths, which is what I'm showing in panel C and D, labeled solar wind and iogenic here. From this, we can then take a difference of the thin to thick filter in both the solar wind and iogenic case, as well as a ratio in both of those cases. And that kind of simplifies into this little table I have at the top center. For the northern aurora, in the solar wind charge exchange case, if we are observing through the HRC-S thin filter, we would expect to observe about 1.51 times more counts than we would through the thick filter. In the iogenic plasma charge exchange case, we would expect to observe slightly more counts in the thin filter versus the thick filter, and we get a ratio of about 1.58. So now that we have these numbers, if we can implement this in practice with real data and estimate that thin to thick ratio, we can determine how close our observations are to this theory, and therefore put some limits on how much solar wind charge exchange and iogenic plasma charge exchange are happening at Jupiter. Unfortunately, this is easier said than done, in part because over so I can see my legend, in part because Jupiter is a moving target. If you train Chandra at one fixed pointing on the sky, a fixed RA and deck, Jupiter is going to move over the course of an observation, especially if that observation is 10 hours, 20 hours, 30 hours, multiple Jovian rotations. On top of that, Chandra has a dither pattern, which is illustrated in all of these figures that I'll walk through in just a second, which normally doesn't matter if you're trained right on the optical axis, but as we're pointing off axis near that boundary, this dither actually means we're going to come in and out of the thin and thick filter as a function of time. So in these 6 different observations we have up here, the first figure I'm showing in each is kind of a zoomed out view of the HRC-S detector on the sky. And then the panel to its right is a zoomed in kind of clip of the same image. In all of these, the orange circle represents Jupiter's real location on the sky, and the kind of red patterns you see are the dither pattern combined with Jupiter's motion on the sky. And you can see in all of these across the top, where we're targeting the thin filter, we actually move in and out of the thin filter and into the thick filter as a function of time. And different parts of Jupiter are on different parts of the detector at different times. So we have to account for all of this if we want to determine which photons were measured by the in the UVIS thick filter and in the UVIS thin filter. So we can do that, and we can back out maps of the emission on the planet Jupiter as it appears on the sky like this. These first 2 images on the left, this column, happened much earlier. Jupiter is much closer to the Earth, and so its apparent size on the sky is larger. These are also, especially the first one, a longer observation. So we have a wealth of thin filter photon detections there in purple. Across the rest, we actually spend relatively little time in the thin filter owing to this dithering and the motion of Jupiter. So we have a lot more thick photon detections in, or thick filter photon detections shown here in black, but still some in the thin filter shown in purple. What we've done next is take each of these kind of columns from this slide as one observing campaign. All of these observations were taken about one Jovian day, about 10 hours after one another. Thank you. And since the first is primarily in the thin filter, or at least partially in the thin UVIS filter, and the second is only in the thick filter, we can generate light curves of both and compare them to back out a ratio. Now here, rather than showing a light curve in seconds, or kiloseconds, I've instead binned it as the central meridian longitude of Jupiter. This is the longitude on Jupiter's surface that is directly aligned with Earth. So if you traced Earth back to Jupiter, it's the longitude that the Earth's kind of footprint would lie in. Because Jupiter is rotating, this is effectively a quasi measurement for time, but it allows us to compare the same parts of Jupiter's surface in different observations separated by 10+ hours. We can then split these pseudo light curves into auroral region and disk region observations. So kind of drawing a line to separate the aurora from the main emission of the planet or the body of the planet. And when we do that, we get something that looks like this. Here in red is our observations that alternate between the thin and thick UVIS filter. In blue are the thick filter observations only. In the middle is the auroral region, and on the right is the disk region. And you can see the ratios that we're getting in the bottom kind of residual panel here. So for our first observation in the auroral region, we get something like a ratio of 2.6. In the next 2 observations, we get something right around 1.8, doing the same technique. And then finally, in our last set of observations, we get a much lower ratio. Our auroral ratio and disk ratio actually look very similar here. But that's to be expected. If I go back to what our observation of Jupiter actually looked like on the sky here, north in all of these images is directed upwards. So we're actually catching just the very southern limb of Jupiter in the thin filter through this observation. So we're not going to see any northern aurora in the UVIS thin filter here. So the fact that these two numbers are comparable is actually a good kind of check on what we're doing. Now, what we've measured is really the emission in the UVIS thin and thick filter, alternating between them, over the UVIS emission in the thick filter only, or the emission in the UVIS thick filter only. So we can do a little bit of algebra here to kind of back out just a thin over thick number rather than a thin plus thick over thick number. And if we do that, we end up with an emission ratio right around 1.6 for the northern aurora. Granted, we only have really 4 observations going into defining this number, but that puts us right in line with what we would expect for a predominantly IO charge exchange driven aurora in the northern hemisphere. It's a little bit higher than this nominal value, so we could say that it slightly favors the IO charge exchange, but enhanced solar wind conditions, enhanced solar wind density could easily up that solar wind charge exchange value. This also does not account for changes between successive observations. So we observe Jupiter once every Jovian day. The aurora can change dramatically on the course of a Jovian day. And so we're kind of assuming that the bulk aurora stays the same day to day, which is not necessarily a good assumption. But that kind of summarizes where we are right now with our early results. There's a lot of other kind of things you can look at with this data set. 2 key ones we want to pay attention to are investigating the 2-dimensional latitude and longitude spatial morphologies of the X-ray and the XUV plus X-ray. I'm showing those on kind of latitude versus longitude maps on the left. And then as well, as I alluded to on the last slide, we want to investigate how X-ray and XUV plus X-ray, or thin plus thick filter, light curves compare on very short time scales. So here, in this observation that I'm kind of summarizing again, we're ducking, the northern aurora is ducking in and out of the thin and thick filter as a function of time, which means if you generate a light curve, shown in the bottom right, you actually get almost contemporaneous thin and thick filter measurements. But these are very low count measurements, so accounting for them in a statistically accurate way is very difficult. So 2 things that we plan to address in the future. And with that, I'll take any questions or comments.
Thank you, Matthew. Very interesting. Do we have questions from the audience?
So, I mean, you're interested in like the 0.1 to 0.3 keV energy range, I think, roughly, if we're speaking in energies rather than lengths. What's at slightly higher energies, you know, from the rest of the Chandra stuff, we know that our theoretical models aren't great at sometimes. How well constrained are you there? You know, which leads into the get to your 1.58 value.
Right. We are not especially well constrained there. So the models are imperfect. The fit that we have to XMM Newton spectra is also based on a very small number of spectra. A follow-up campaign with simultaneous XMM coverage to kind of compare directly the real spectra that we observed, extrapolate it down to lower energies, and then measure what we're seeing in the thin filter would put much tighter constraints on those numbers.
Anyone?
So I believe you have about 1 megasecond at a time for Chandra, right? At what point can you start doing observations? So this is going to take a while. I mean, analysis? Because it's gonna take a while to observe that much.
Sorry, could you repeat?
Sure, so
Yeah.
you've got 1 megasecond of time.
Sure.
The maximum we can observe with HRC right now is about 15 kiloseconds.
Sure.
And then we have to go source. That means that you've got north of 70 observations. And that's gonna take some time to do, especially because it's also a moving target and all that. So my question is, when can you start doing the fun things that you're telling us you're gonna do? With that data, do you have to wait for the full 1 megasecond to be observed, or can you start working with, half a megasecond?
Sure. So it's really a question of what sorts of errors we're comfortable with here. We can take individual observations, especially where we're kind of ducking in and out of the thin filter region, which are only about 10 hours here. I believe we cover one Jovian day only before being off target. If we had a really good understanding of exactly where our photons were coming from and nailed down sort of what the PSF that we're expecting is, to have a better understanding of these light curves that we're generating, we can extract information from just single observations, very short observations. The biggest benefit here would probably be incorporating other data beyond HRC-S into our analysis.
Thank you. Do you see any question online? No. Any more questions from here? Okay, if not, let's thank both our speakers of today. Okay, as a reminder, we've got a seminar next week to is your preparation and final drafting to the annual staff proposals. So we will see you in 2 weeks.
Yeah, and yeah. Or speaker for 2 weeks from now, so if anyone wants